Okay, today we're going to talk about dilations. Dilations can be found in 9.6 in your textbook. So the figures that I'm using right now are clipped directly out of your textbook. First thing I want to say is just to remind you before we start talking about the dilations, what we've already talked about, and that's the translations, the reflections, and the rotations. Now, notice also that I've used capital R for reflection and lowercase r for rotation. That's not a typo, it's on purpose. Remember when we do the notation for translation, we use capital T and then XY down here. For reflection, we use capital R, and then down here we put whatever we're reflecting around. And then for rotation, we use lowercase r, and then we usually put the degree and then the point of rotation, which for us is going to be the origin. Okay, so these are all considered rigid transformations or isometries, and it's because their size and shape does not change, only their location on the coordinate plane or on the geometric plane. So they maintain their size and their shape, the angles, side lengths, and everything stay the same. Today we're going to talk about dilation, and in dilation it's a little bit different because the size of the figure does change. However, it changes by a given scale factor. So if the scale factor is 2, then all the sides are multiplied by 2. Or if the scale factor is 1/2 because it's being reduced, then all the side lengths are multiplied by 1/2. And the angles stay the same. Okay, so just our side lengths change. First thing I want to talk about, or first example of dilation, is your pupil, because we're all familiar with that, and lots of us have had to have eye exams where we had our pupils dilated. And you notice that normal light, the iris shows and the pupil is smaller, and in dim light, or when we're having our eyes dilated, the pupil is larger. And this is, of course, to let more light in. And for the eye doctor, this allows them to be able to see into the back of your eye. It's kind of like a bigger peephole, if you will, to the back of your eye. So they dilate them so they can get a bigger area. So you notice that the diameter of our pupil here is 2 millimeters and the diameter of our pupil here is 8 millimeters. So therefore the pupil has become larger. So we say this is an enlargement. Okay. In order to find the scale factor in which it enlarges, we always do image over pre-image. So if you remember which one's which, the pre-image would be before the transformation and the image would be after. So we would say that the diameter before, right, is going to be 2 and the diameter after was 8. So our scale factor is 8 to 2, which we know actually will reduce to 4 over 1. Okay? Now, because our scale factor is greater than 1, we know it's an enlargement even if we weren't looking at the picture, because greater than 1, a scale factor greater than 1 means it gets bigger. And if we were going to go from dim light to normal light, then we would have done it the other way and we would say 2 over 8, which is 1 over 4. And that would give us, 4, that would give us dim to normal, right? And this one right here obviously gives us normal to dim. Okay, so if we look at an actual dilation with a geometric figure, we're going to use a central point or a common point of C. And we're going to measure the distances from C to R and from C to R prime so that we can get this scale factor, this relationship between the two. Okay, and notice in our key concept what we've said is that this image has been dilated from point C, right? Which means this is the pre-image right here, and this is the image, okay? So it went from here to here. This is what's going on, right? And that the angle measurements are preserved and just our side have changed, right? So in order to get our scale factor, we would use image right, which is this one, right, the after, over pre-image. So we would just pick like C to R and C to R prime, right? So C to R prime would be the distance for the image, and C to R would be the distance for the pre-image. Now, what we also know is that if I did the same exact thing from C to P prime and C to P, I should get the same scale factor, right? Because each of them are being dilated to the same factor. Okay, so we look down here, let's try it with numbers. Now be very careful with this one when we have images within images, because if you notice, they're telling us that from x to t is 4 and from t to t prime is 8. So if I actually want to get the distance from x prime to t prime or from x to t prime, I have to add this 4 and 8. So that distance is actually going to be 12. So I'm going to use the same scale factor, image over pre-image. So the image is x to t prime, right? Okay, which would be what? 12. And the pre-image is going to be x to t, which is 4. Okay, and we know that that will reduce, right, by a factor of 4, and we'll get 3 to 1. Now this is a ratio, so we can write it as 3 to 1, or we can actually write 3 to 1, right? But the scale factor is going to be 3. Okay. Now, the other thing that we have to remember is that if we have a scale factor that is greater than 1, it's going to be an enlargement. And if we have a scale factor that's less than 1, or a fraction, then it's going to be a reduction. So those are the two terms that we need to make sure we know, enlargement and reduction. Okay. Now, the other thing that we have to know from this section is how can I do it on a coordinate plane? And just like the other ones, we want to do one coordinate at a time. So if I'm going to dilate by a scale factor of 2, see the notation capital D, right? And then this is scale factor right here, right? And then this is the image, whatever we're going to dilate. That's how we notate it. If I'm going to dilate PZG, triangle PZG by 2, this is what happens. I'm going to take the coordinates of P, Z, and G, and I'm going to multiply each of them by a factor of 2. Okay, so I would say P is 2, negative 1. So if I multiply 2 times 2, I get 4. And if I multiply 2 times negative 1, I get negative 2. And then I'll do the same for G. So 2 times negative 2 is negative 4. Excuse me, for Z, and 2 times 1 is 2. And for G, 2 times 0 is 0, and 2 times negative 2 is negative 4. So that should give me my coordinates for my new dilation. Okay, and if we look down here, we have it, and it looks like we've got it. So Z prime is going to be 1, 2, 3, 4, so negative 4, 2. Okay, check. Uh, P prime, which is going to be right here, is going to be at 4, negative 2. Okay, and then G prime is going to be at 0, 1, 2, 3, 4, 0, 4. So that's how we do it. Now, if it were a fraction, we do it the exact same way. If it were a D and it was 1/2 was a scale factor, okay, and we said xy, we would say 1/2 times x, right? And 1/2 times y. Okay, the exact same way. Of course, this one would be a reduction because it's a scale factor less than 1. So you have a worksheet for dilations, so go ahead and fill out the worksheet so that you have some practice problems to work on. And then also we've got, see if I can find the table. And here is your table, so you can fill out your table for the dilations, right? And it's just got a scale factor. I would go ahead and do this problem especially because it's got the 3 halves, so you can work with a fraction. Okay, and that's dilation.